Good morning, everyone. We're Team 22, and we are here to present our SSD security protocol verifier that we all built throughout this last month. So our end architecture was to have a hybrid state machine plus an agentic LLM verifier, and then we'll share our ablation study that we applied to our architecture overall. Our presentation title is our one-line takeaway from our entire project, and it's how cross-check is all you need, whether or not it may be you're creating a data set from your architecture or whatnot. So basically, this diagram is our entire architecture. The rule-based Oracle carries the task, and tool-based LLM agent is only used at the frontier tasks where rule-based Oracle fails to make a verdict. So upon receiving input trajectory as an input, it goes through an event source reducer. And state here only advances on successful operations that is verified by the Oracle. And after that, the rule-based Oracle resolves the verdict if it can resolve it from the rules that we previously implemented. If the Oracle abstains and decides that it cannot decide whether or not this output is verifiable by the rules, then it falls back to the LLM agent. The LLM agent then uses the tools that we implemented, the first being the Oracle state tool, the second being the spec document fetch tool, and it cross-checks every step alongside the way of its reasoning to make the final output verdict. Note here that our the rule-based Oracle is the basis of our accuracy, and it resolves more than 80% of the test cases that we actually had from our submission server. And then only the rest and the small percentage of it was resolved by LLM agent. And both combined results in an output verdict. So here is a simple progress graph of how we achieved 92.0 at the end of the day. So milestone by milestone, we started at 52.5 with a pure prompted LLM baseline that was provided to us as a skeleton code. The biggest single jump, plus 28 points to 80.5, came from adding the deterministic Oracle. The spec-grounded rules took us to 90.5, and the fail hypothesis structure, which I will explain further on, took us to 91.5, which was the deterministic ceiling. We tried every different rules to improve the accuracy simply by deterministic terms, but we hit a ceiling and we couldn't see any improvement for the past 3 weeks simply by adding rules to the deterministic Oracle, and that's when we decided that we actually needed to fall back to LLM agents to have a better accuracy on the leaderboard. And in the end, we implemented a tool-based LLM agent, which took us to 92.0, which allowed us to be at the top of the leaderboard at the end of the project. So the point of this graph is that no jump ever came from having a bigger model or having a fine-tuned model. The rules did most of the work, and the cross-checking process did. So our first layer of our architecture is our deterministic Oracle, as I've emphasized before. It's basically an event source state machine. So each record is parsed, and the state updates only upon successful operations, and then we compute the spec required response, and then compare it with the input trajectory result that we achieved as an input. And it returns pass, fail, or none to abstain. And every rule lives in a named fail hypothesis bundle such that coverage and failure modes are easy to audit. And 3 regression harnesses guard every change, and we merge the rule only when it's a net gain on our 4,000 case labeled set with 0 regressions. So the public dataset that was given to us only had 20 datasets, which we all know that is not enough to either fine-tune a model or build the Oracle. Therefore, we thought that building a verifiable local dataset was a must if we were to actually perform better with this task. So with 2 rules, we built our own local datasets, and the 2 rules are as follows. The first rule is that the input must always be a raw trajectory JSON, and other information that we add to our local data sets, such as labels or spec or hypothesis IDs or whatnot, never leaks into the Oracle or the agentic LLM when we actually put our local data set as an input. And the second rule, which is the most important, is that every label must be verifiable via Oracle or artifact. So we put our own LLM agents in a continuous cross-check circle such that they verify the test data sets very closely via Oracle or artifact, and we enforce them to input the verifying evidence to cite them into within the dataset. And we created 2 versions of the dataset, and the first version goal was to create as much data as possible. So with the 4,000 seed cards that we used in the previous slide to create a regression harness, with that we created 60,000 train rows. And our version 2, which was a distilled version of the version 1, we had 7,900 train rows. And our goal here was to have fewer but cleaner data set to preserve label fidelity and prioritize anti-memorization. So let me briefly talk about our second approach to the LLM agent. So upon starting this assignment and achieving like 91.5 with the deterministic oracle only, we thought that deterministic oracle could be the only solution that we need for this project, but then it turned out that it clearly showed a ceiling. So no matter how much we improved on our deterministic oracle on a local data set, the submission accuracy couldn't top 91.5. So we thought that the abstain cases where our oracle would say none had to be resolved with LLM agent, and we tried 3 types of approaches. The first being, we tried to optimize larger models that wasn't provided to us within the skeleton or the submission server. So we tried to optimize GPT OSS 120 billion, which didn't really work out because of the network speed of the submission server. The second approach we took was to fine-tune the QEM models that were provided to us. The third approach was to try a tool-based LLM agent without fine-tuning and just Quen 3.6, and we customized 6 tools to use while reasoning. To give a little spoiler first, the third approach is what we took at the end of the day, and let me explain to you why the second approach didn't work out. So the second approach that we tried was to fine-tune the QEM models that was provided to us. And fine-tuning clearly showed a ceiling not long after we tried this approach. So fine-tuning the weights did converge, but it overfit the prompt and making it made it unscalable. So basically, yes, fine-tuning converged, but it overfit the prompt, and classic catastrophic forgetting occurred. The model stuck so hard to its training prompt that a small change in instructions tanked accuracy, so it didn't generalize. So Snell and colleagues from the prior works showed that scaling test time compute can beat scaling model parameters. So we decided that instead of fine-tuning the weights, we spent the compute on reasoning, long reasoning up to 60,000 tokens per trajectory, and cross-checking every verdict alongside the way.
So up to this point, our deterministic oracle did most of the heavy lifting, but it had a ceiling at 91.5. The remaining cases were the ones the oracle abstained on, and for those, we needed the LLM agent to make the call. The key question was how do we let the agent access the ground truth, the artifacts accurately and efficiently? Our answer was grounded in React from iClear 2023. The core idea is simple but powerful. You interleave verbal reasoning traces the model's thoughts with task-specific actions, where the model accurately reads from external sources. This combination does 2 things for us. First, it reduces hallucination and error propagation that you get from pure chain of thought. And second, it outperforms baselines on decision-making tasks while staying interpretable. We can actually see why the agent reaches its verdict. To make this real, we built 6 custom tools, an AI-native environment for the agent. Honestly, the most powerful, important ones turned out to be plain Bash and Python. The agent just grabs through the docs and dataset on its own. The other key tool is Oracle State, which returns the reconstructed state but never a verdict, so we don't bias the model toward the Oracle's answer. The rest, decode UID, decode column, and find spec, cut down search time, and give a one-shot view of the whole document structure. The whole philosophy here is cross-checking. The agent verifies every decision against 3 sources at different confidence levels. The artifact docs at 100%, essentially grounded truth, the Oracle state at 90%, and our local dataset at 80%, so we never trust a single signal blindly. Once the tool-based agent broke through the deterministic ceiling, we tried to push even further with 3 more approaches. First, we let the oracle abstain more aggressively, since we now had a trustworthy fallback. It could differ when unsure. We didn't see a clear accuracy gain, but we kept it. Second, we tried a higher level abstraction, a pure summarized spec digest tool to save the agent from grabbing raw docs. That actually hurt accuracy, so we dropped it. And third, we add Vo3 for self-consistency to deal with the agent's non-determinism. but the time and stability trade-off just wasn't worth it. The lesson, as we like to put it, peak tuning is no tuning. 튜닝의 끝은 순정이다라고 말할 것 같습니다. Modern motors are already so well tuned to a native Bash and Python that our custom abstraction just got in the way. Sometimes the best move is to get out of the model's way. Finally, our oblations. Internally, our tool-based model evolves at around 89%, while the 9B LoRa only scored 73. On the leaderboard, Absein's fail gives 91.5, Absein's success drops to 91, and the 9B LoRa fallback only hits 90.05. So fine-tuning was actually worse than a simple heuristic. Flipping all resolved verdicts collapsed to 9, confirming the oracle was generally right. But the winner, rule-based oracle with the tool-based agent as fallback, lands to 92. So in short, cross-check really is all you need. Thank you.
네, 질문 한번 빨리 하고 다음 팀 나와주세요. 연결. 네, 제가 할게요. 그럼 폴백은 얼마나 자주 하게 되나요? 보통 아니 룰이 다 하는 거야? 아니 뭐
내부 저희 리더보드 상에서는 거의 저희가 보기로는 폴백이 한 20케이스
그러니까 퍼센티지로.
한 10%.
아, 오케이. 네, 그 시간이 부족해가지고 네, 다음 팀 빨리 나와서 연결해 주세요. 시간 없어요. 미안해요. 슬라이드 뭘로 만들었어요? 아, 수작업으로? 아, 대단하군요. 질문은 오늘 강의도 있어 강의를 좀 최대한 빨리 끝내고 몰아서 받겠습니다.
Hello everyone, my team is Team 1 and we are going to introduce the selective 3-border model. Our final system reached 91.5% and finished in top 3. It combines two deterministic rule engines with QLORA border. The important point is that we did not run the large model on every example. We used it selectively only where the two rule engines could not form a majority by themselves. The standalone scores were 90% for voter A and 84% for B and 86.5% for C. The final three voter ensembles reached 91.5%. To understand the 1.5 point gain over A, we divide the hidden cases by A and B agreement. When A and B agree, their answer already has 2 votes, so C cannot change the majority. Every possible gain or loss therefore occurs only when A and B disagrees. Both A and B were produced with an LLM from the same detailed prompt, but both execute as deterministic Python programs during inference. A is stronger method status oracle at 90.0%. B is an independent rule-based re-implementation at 84.0%. The three main differences in their rule coverage are KGRK semantics, ambient treatment, and ACL chain breakdown. Because these rules are implemented differently, A and B disagree on small but useful subset. These are exactly the cases where C can contribute to a deciding vote. Engine A and B separate state reconstruction from final status prediction. It replaces all previous successful steps through apply underbar asterisk functions and maintains a symbolic protocol state. The state includes the current session and SP, authenticated authorities, C pin credentials, locking ranges and bits, keys, and beer states, and access control data, and etc. For the final step, A and B computes the single specification correct status and compares it with the device response. The deterministic reply and judge structure produced pretty well scores. This slide shows how we generated one training example for voter C. First, we create a random but valid sequence of TCG commands and replay it through protocol state. This gives a consistent current state, such as the active session, authenticated authorities, credentials, locking ranges, and MBR state. Second, we sample one plausible final method, including its target UID and arguments. Third, engine A calculates the status code that it expects for this state and method. We then create a pair. The prompt contains the state, relevant facts, rule, and final invocation, while the goal completion contains the reasoning and final status. We generate 20,000 of these prompts completion pairs using Python. The LLM does not receive the raw protocol trajectory without explanation. Instead, its output is organized into 4 blocks. The first block is a compact state summary. The current session and SP, authenticate authorities, tracked pins, and locking ranges and MBR state. The second block contains state-derived facts, such as whether the request targets the correct SP, whether the session is read-only, and whether the credential matches. The third block is the micro-reg rule selected for the current method and target table. The fourth block describes the final invocation, its method name, object UID, and record and optional arguments. Training and inference use the same instruction for block body and status code. Voter C used a 4-bit Gemma 431B based model with Q LoRa adapters. The LoRa configuration used rank 8, alpha 16, dropout 0.05, and the Q, KV, and O projections across 60 text decoder layers. The selected checkpoint was step 750 with a loss of 0.0018 and the hidden score of 86.5%. Training longer reduced the loss but hard accuracy. Step 1000 scored 80% and the step 1500 scored 81%. We thought that the model starts reciting the rule paragraph instead of applying its discriminator chain. At inference time, A and B run first on the full evaluation set. If they agree, the shared verdict is returned immediately and voter C is not loaded. If they disagree, voter C is lazy loaded and C supplies the third vote. This is exact 3-way majority voting. For TCG method cases that reached neural generation, the local runtime was about 15 to 19 seconds per case. Non-TCG read, write, and reset commands bypass neural generation inside C. The final ranking was clear. B scored 84.0%, C scored 86.5%, A scored 90%, and the ensemble scored 91.5%. That is a gain of 7.5% over B and 5.0% over C and 1.5 point over A. Because improvement is impossible in the A equals B bucket, the gain proves that the combined B and C majority corrected enough of A's mistake on disagreed subsets. Free choice mattered most. First, teacher quality mattered before scale. Fixing one trajectory training pattern left 0 oracle target mismatches. Second, diversity mattered more than standalone scores. The weaker 84% voter remained useful because its implementation failed differently. Third, stopping at the golden window mattered. Lower training loss did not mean better hidden accuracy. Thank you for listening.
다음 팀 빨리 나와주세요. 생각해봤는데 그냥 우리 카톡방 있으니까 저기 아까 그 질문 있었던 학생 있죠? 카톡방에 아까 팀 몇 번이죠? 네, 이 팀한테 질문을 해주세요. 그리고 여기 두 번째 팀한테도 질문 있으면 카톡방으로 해주고 카톡방에서 답장 좀 해주세요. 지금. 답해주는지 여기서 볼게요. 두 번째가 팀 1이었고 첫 번째가 팀 몇이었어요? 22. 네. 그러니까 뭐 팀 몇한테 찍어서 질문 여기 적어주세요.
뭐가 떴었는데 사라지는 원래 떠야 돼. 예, 원래 떠야 돼. 인식이 안 돼. 이거를 딴 거.
Good morning, everyone. My name is Seung Jae Bang in Team 2, and our teammates are In-hyuk Park, who is the second speaker of this presentation, and Jin-young Park and Dong-hyun Lee. Our presentation will be held by these two parts. The first part, which will be spoken by me, would be about how we made our rule-based model and how we made our test cases, which will be called TC from now on. And the second part, which will be spoken by In-hyuk Park, will be about how we train our AI model. So even though Team 22 and Team 1 already briefly talked about our project, but for a brief recall, our original mission was to determine whether the last response of SSD for given each trajectory commands were right or wrong. So what would be the most natural idea to make this problem solvable? In my opinion, the most natural idea would be make a perfect rule book and determine. And that was the exact first idea we had. Our strategy was as follows. We first normalized row UIDs and byte strings into symbolic names. Then we replay every non-final command and update the internal state only when the observed response shows the operation actually succeeded. From this replay, the solver infers the state right before the target command. Finally, for the last command, the model predict what the SSD would have responded and compare them. If they match, we output pass. If they don't, and we output fail. But so we put the rulebook we got and this strategy to LLM and ordered the LLM to make a rule-based model that reflects as many rules as it can. But as you know, we cannot get a perfect rule-based model at the first shot. We needed feedbacks by running that generated rule-based model on some verifiable test cases. But we noticed that we only had 20 test cases. 20 is too small, right? So what we did next is to make some good test cases. We first simply put the rulebooks we have to LLM and make some simply rule-based test cases. But unfortunately, by simply putting the rulebook, LLM performed very badly. It only made some biased test cases, which allowed us to test only few rules. So we divided our rule books section by section and put them part by part to LLM and made these three test cases. This ETC, SPF, UCT are the name of sections. But there was a problem. We didn't know what's going on. Since the number of the test cases were too large, we couldn't control them one by one. So we thought that we need some test cases that is under our control. So recall that TA said that the comments except for the last line are 100% accurate in public 20 test cases. So we tried to use those. We first randomly selected intermediate line and cut off the comment lines after that. We used the selected line as a new test command. So for some cases, we generated that case by just leaving the selected line or simply flipping success or fail to have 100% accurate answer. As you can see here, the case number 1 is generated in that fashion. And the other cases are generated by changing only the last comment slightly, which makes the generated cases under our control, which is that second cases. So let me skip these examples because we are running out of time. So with those test cases, we made our AI agent to repeat to make rule-based model and run them on generated TCs and refine them. So as a result, we could get a rule-based model with high accuracy. So that's it for the part 1 and part 2. give your presentation, please.
Okay, so far we've seen the rule-based verifier and how an AI agent helped us build the rules. And the second half of this presentation looks at the opposite direction. Can we make the AI actually generate the verdict itself? We tried two strategies, and the first one was just simply fine-tuning using LoRa. So we took Quen, the smallest version, which was 3.5 and 0.8 billion. So we tuned it on 2,500 bounce cases from our generated pipeline. The training input was simply just the command response prefix plus some additional symbolic state text from the rule replay, and what it gives us as an output was not only just a simply pass-fail label, but the expected response and the family of the rules that was violated. So our model additionally predicts why it fails, just then whether it succeeds or not. So yes. Yeah, so the role of the model we need to point out is that it's an ablation judge. It proposes a verdict, but it never overrides the exact rule oracle in the final tests. And our second method was graph rag. So initially, the naive approach dumps long spec text dumps into the model as a prompt, which we thought was inefficient. Instead, we built a graph of protocol states and rule clauses, such as session state, authority, etc. And for each final command, we only retrieve the connected subgraph to optimize the prompt length and the tokens, etc. So the judge finally gets a small focus evidence packet instead of entire pages of text. So we currently have 3 systems to test and compare. And let me set up how to score them. Instead of cherry picking or additional separate synthetic benchmarks, we just simply use the public leaderboard score and that only. So, because it was the only genuinely true thing we had. So we had 4 versions of submissions. So the first one was the rule-based verifier we made, and the LoRa and the graph rag. So, and the final hybrid version was the mixture of the 3. And here's where we landed on. So the highest score we got was a 90.5, which we got from the rule-based verifier. And well, the results were kind of counterintuitive for us, because even though we tested various methods of AI variants, the best method we got was the rule-based verifier. Even the hybrid model, adding a layer of AI on top of the rule-based verifier, only lowered the score by 3 points instead of getting up. And pure LoRa or GraphRag got even worse, 81.5 and 77.5. So as a conclusion, we can state out these 4 points. So first of all, state replay is the core. We in order to predict the verdict, we essentially have to read the entire context. Partial context will only get you so far. And also, if we're going to generate data to train the LLM or AI agents, we basically have to maintain a balance to avoid one generator dominating over the other. And even though our LoRa and GraphRag AI methodologies were valuable, just to look at the scores, the leaderboard just gave us that the pure rule-based verifier was simply just best. And yeah, that's the end of our presentation. Thank you.
수고했어요. Okay, it's interesting. That they found out rule-based model performs best, and if you mix AI, it starts to deteriorate. How about opinion from Team 22? You guys said you route 10% of queries to AI, and it actually helps. What was the key to make AI improve the accuracy? Can you just come up? Yeah.
I think giving LLM freedom to search around documents and dataset was the key to improve, make it improve, but by doing so, the inference time took to get the answer per trajectory was really slow for our team. It actually generated about 40 to 60k tokens per trajectory to get one answer. So it checks all the specs and get search around the data set and retrieve again the spec documents and so on.
무슨 말인지 잘 못 알아듣게 한국말로 좀 쉽게 설명해 주세요. 그러니까 세 번째 팀은 AI 썼는데 성적이 떨어진다. 근데 여기는 10%의 쿼리는 AI 라우팅을 했다는데 성적이 오른 건가요? 아니면 차이가 없었던 거예요? 오른 거 맞아요? 오른 거면은 뭐 때문에 오른 것 같다. 룰 베이스에 비해서 AI가
결국은 룰 베이스로 저희가 모델링 할 수 없는, 그러니까 그 형식이 딱 정해져 있지 않으면 룰 베이스로 모델링 하기 되게 어렵다고 생각을 했고, 그렇기 때문에 저희는 마지막에 룰 베이스에서 오히려 룰을 걷어내는 작업을 되게 많이 했습니다. 그래서 그 룰 베이스에서 에이전트로 최대한 많이 넘겨가지고 에이전트가 직접 트래젝토리 보고 러 트래젝토리 보고 스펙 탐색하면서 근거를 찾을 수 있도록 유도를 많이 했습니다. 근데 이제 그렇게 하면서 저희가 이제 파인 튜닝 이런 거를 전혀 안 했기 때문에, 그러면은 완전 에이전트 그 능력 자체로 돌아가야 되는데, 그렇게 하기 위해서 얘가 툴콜을 거의 한 100번을 하기 때문에 되게 오래 걸리는 단점이 있긴 했습니다. 근데 뭐 저희가 에이전트를 성능을 잘 나오긴 했어서 그거를 채택하게 된 것 같습니다.
Okay, so in the remaining, I wish I had more time to give lectures, but I heard some people have tests on Wednesday, so today has to be the last day for the lecture, unfortunately. There are tons of stuff that we didn't cover. Deep learning is fast changing, but I tried my best to cover the up-to-date material. And one thing we didn't cover is KB cache compression. So last time we talked about neural network pruning and quantization. And in addition, what we really need to do, if you want to make a service out of this, is we need to think about how to manage the KB cache. So as you know, when input comes in, so X may be the raw tokens or embedding from the previous transformer block. You multiply by WQ, WK, WV, and you maintain these KB caches for all the previous tokens. And it keeps stacking up without a limit. And at some point, you're going to hit the hardware memory limit. That's one thing. The other thing is your decoding latency is going to be very slow. So in order to create a single next token, it has to attend to all the previous KB cache. So the more KB cache you have in the memory, more things you have to attend to, and it's going to slow down the decoding latency. So how do you go about this? You need some code or mechanism so that you can evict less important KB cache from the memory. So that's what we're going to cover today. That's called KB cache compression technique. So just to give you an illustrative example, we went to XLamma v3 GitHub repository. Has about 500,000 tokens. And it came up with certain questions that you really need to understand and to answer correctly. So for example, what is the maximum tokens to be a multiple of when creating a cache? The answer is 256, and etc. One thing you can do is just KB cache or prefill README file, which has a lot less tokens, and you do a question answering, and all of them is incorrect. But in terms of the KB cache memory, it's only about 100 megabytes, and decoding speed is fast. It takes about 8 milliseconds per token. If you do full KB cache of 500,000 tokens, you answer everything correctly, but just the KB cache memory itself is about 27.5 gigabytes, which is a lot. Decoding latency is extremely slow compared to 8 milliseconds. It's about 50 milliseconds. Extremely slow. So this is one of the reasons why memory companies are having all-time high stock price value, because the need for the raw memory is quite significant. Majority is coming from KB cache. Well, also the large language models. So if you run KB cache compression technique, you can answer everything correctly, but reduce the KB cache memory significantly, like 3x or 4x, and cut down on the decoding speed. So this paper came up from our research group, and it was selected as oral presentation at NeurIPS last winter in December. It was among top 0.3% papers accepted to NeurIPS. Okay, so in the interest of time, I'm going to speed up a lot. Okay, so as we all know, as we increase the sequence length, and as we keep discussing or using LLMs, these KB cache just increases linearly. So, yeah, in the interest of time, I'm just gonna make it very brief. So what are some existing techniques? Some existing techniques, given some large context and a question, you prefill everything, including context and the question, and you do some form of KB cache eviction, and using that lightweight KB cache, specifically tuned for that question, you decode to answer. So what's the downside? You need to do repetitive prefill per query. That's going to be very slow. And the proposed framework is to make it more practical. You want to only prefill once and evict once. So given an extremely large context, using the context only without looking at any queries, how do you prefill them once, evict once, and come up with a lightweight KB cache that can serve many questions? So for example, in the enterprise scenario, this could be something like, for our project, some spec documents for hardware or something like this that's shared among engineering teams. So can we prefill all these spec documents, evict once, So we have a very lightweight KB cache that can answer any questions. So without even looking at what the user is going to ask or how to interact, how do we evict or distinguish which KB cache is important and which KB cache is not important? So the main idea is compressed KB cache and LLM should retain all the full contextual information. So here's the main idea. So for this paper, there's absolutely no equations. The idea is what got it accepted as oral presentation. Okay, so here's the idea. You have extremely large context, and if we evicted KB cache in such a way that important things are preserved, less important things are freed from memory, then it must be the case that when we request LLM to recite the context, you should be able to decode the original context, or in other words, reconstruct the context. Okay, once again, given the evicted KB cache, if it was done precisely, and then we prompt LLM, okay, can you, so something like this, okay, can you recite the previous context? And if it's good, then it must be the case that we evict the KB cache in such a way that the memory is preserved. So that's the single idea. Rest of them is technical. So the high-level overview is we have large context, we pre-fill once, and then we provide a very specialized command. Please decode or please recite the previous context, something like this. And provide the context again and measure the max cross attention. I'm going to explain this later. To somehow measure the importance of each KB cache across all the heads and evict KB cache that has low score. And using this evicted lightweight KB cache, serve many queries. So here is how we're going to measure the importance. So the green parallelogram is for the previous context. And, okay, same thing here. This is the specialized command, repeat prompt, please recite the previous context. And we insert the original context again. And we measure the max cross attention. So this axis here is number of heads. This is the context length. So for a given query, what is the token that has maximal attention? That is the number here. Does this make sense? So here we provide the repeat context and ask LLM to regenerate or reconstruct the context. And when it's decoding the previous context again, some of the context tokens are going to receive a lot of attention. Some of them are not going to receive attention. So let's say this guy has a lot of attention, say, I don't know, 0.7, and this guy has max attention of, I don't know, 0.001 or something like this. And this guy has 0.0001, where we take the max along this direction. So what is the intuition here? So when we're reconstructing, some of the tokens don't receive any attention from the context tokens. So it must be the case that when we reconstruct the context tokens, it's possible to reconstruct it even if we don't even know what that token is. So based on the tokens to the left and right, you may be able to accurately infer what the token was. So as is, this is completely impractical because we're doing this because context is very large, but we need to plug in the context twice. So this is, as is, this is useless. We're doing this because it's really hard to fit this into the memory. So what we do is, to make it practical, we give it pieces or chunks of context and use the repeat prompt to do to compute the submatrix of this whole matrix. And that's most of the idea. The critical thing is we ask LLM to regenerate the previous context, and some of the KB cache that don't get much attention, we just print it away. And how much can we print it away? Up to 3x or 4x without performance degradation. So here are some results. For a variety of tasks like retrieval, question answering, redundancy, this red curve compares against previous KB cache compression techniques, and we score number 1 on KBPress leaderboard. KBPress is the open repository to compare different KB cache compression techniques. And KBZ compresses the KB caches by evicting tokens and evicting KB cache that corresponds to tokens that don't receive much attention when we ask LLM to regenerate the previous context. So that gives us about 3 to 4x of reduction in KB cache size and about 2x decrease in decoding latency with minimal performance loss. And it's validated on many different tasks like question answering, reasoning, code compression, and yeah, unfortunately, I don't have much time to go into much detail here. Yeah, I wish we had more time to cover more materials, but this is going to be the last lecture. And I really enjoyed teaching this class.